Now, as we've stated in previous videos, redox reactions occur when one substance gets reduced, or it gains electrons, and another substance gets oxidized, or it loses electrons. These two half processes come together to form one giant redox reaction. Now, when we're balancing these reactions, we have to pay attention to two things. The first is that the conservation of mass is observed, where you have the same number of atoms on both sides of the chemical equation. But because they need to occur in acidic, basic, or neutral environments, so we often have to add hydrogen ions or hydroxide ions to our solution, we have to also check that they're electrostatically balanced. When you have an electron moving from one substance to another, you're also going to have a transfer of charge. So we have to make sure that when we've balanced our reaction, it's electrically balanced or electrostatically balanced as well. And to do that, it's a bit of a process. While those processes are largely the same between acidic environments and basic environments for these redox reactions, they do vary a little bit at the end. Remember, when you have a basic environment, there should be hydroxide ions present in the final solution to help drive that reaction forward. Same thing with acidic solutions or environments, except we should have hydronium ions that are present in the final solution. Let's take a look and see how do we approach balancing full redox reactions. So the first step to this process is to write half reactions between related entities. And what we mean by that is that the substance with chlorine or the reactant with chlorine is going to be making a half reaction with the chloride anion, and the substance that is sulfur dioxide is going to be yielding a product of sulfate. And that's because we shouldn't see elements turn into other elements. This is not nuclear decay, this is a redox reaction. Now, to balance these half reactions, we're going to balance the non-oxygen and hydrogen atoms first using the same traditional methods. Then we're going to balance the oxygens by adding water. So you add waters to the oxygen deficient side. In this case, that's 3H2O on one side. And then we're going to balance the hydrogens. And once we balance the hydrogens, we're going to balance the charges. And the only way that we can balance charges is by adding electrons to the proper side. In this case, that's 6 electrons to the left side, which makes a reduction half reaction. For the other half reaction, we're going to do the same thing. We're going to balance the sulfurs first. Then we're going to balance the oxygens by adding water to the appropriate side, which in this case would be to the left side. Then we're going to balance the hydrogens by adding hydronium or H plus ions. And finally, once we balance the non-oxygen atoms, the oxygen atoms, and the hydrogen atoms, we're going to balance the charges. And to do that, we can only add electrons. In this case, we're going to bring the charge of 2 plus on the product side down by adding 2 electrons on the product side, making this an oxidation reaction, or half reaction for that matter. Now, like we said at the beginning of this video, the redox reactions have to be atomically stable and electrically stable, which means that in our final redox reaction, we shouldn't have any electrons or any charged substances that are on either side of the equation. So in order to make sure they cancel out, we have to find a lowest common multiple between the two half reactions. Since our reduction reaction had 6 electrons in it and the oxidation reaction had 2 electrons on the product side, the lowest common multiple is 6. So we're going to multiply the entire oxidation reaction by 3 so that the electrons are 6 and that they'll cancel out in the final accumulated equation. Now, when you multiply one entity by 3, then the entire equation has to be multiplied by 3. That's how these things work. So our new reaction is as follows, where all the coefficients are multiplied by 3. Most importantly, though, the 6 electrons. Now for the final part here, we're going to write both half reactions into one giant redox reaction, and then we're going to simplify it. Now when I say simplify it, I mean that we're going to cancel any like terms that are on either side, or I should say opposite sides of the reaction. And the reason we can do that is because you can think of that yield sign or that arrow as a giant equal sign. And just like in math, if the same variables on opposite sides of the equation, it simplifies or cancels out. So we're only going to do that though if it's the same substance with the same state. It has to be exactly the same. Our final redox reaction then reads 1 chlorate ion plus 3 sulfur dioxide plus 3 waters yields to 1 chloride anion plus 3 sulfate anions plus 6 hydrogen or hydronium ions. And since this is an acidic solution, we can expect that there's hydronium present in the end. And the charges are balanced. And one of the things that you can check, I know this is a long process, but one easy way that you can check if you've done this right is if the charges balance on both sides, you're most likely right. For this next example, we're going to do the same thing. We're going to create a half reaction between H2S and S8, and then another half reaction of NO3 minus to NO. And we're going to balance each one according to the rules of balancing half reactions in acidic solutions. Again, to do this, first we're going to balance all the non-oxygen atoms. Then we're going to balance the oxygen atoms by adding water for every oxygen that is needed to the appropriate side. Then we're going to balance the hydrogen atoms by adding H plus to whichever side needs hydrogen, and we're going to make sure that that's on the appropriate side. Lastly, we're going to balance the charges. And remember, we can only balance the charges by adding electrons to the appropriate side. If we do this properly, one of the half reactions should be a reduction reaction, and the other should be an oxidation reaction. Now to make sure that our electrons cancel out in the final redox reaction, we're going to find a lowest common multiple between the two half reactions. In this case, that'll be 48. So we're going to multiply the first half reaction by 3 and then the second half reaction by 16. And once again, we must multiply everything in those half reactions by those coefficients, not just the electrons. Now we simply combine the two half reactions into one giant redox reaction. And like in the previous question, we're going to cancel out like terms on both sides. The final simplified redox reaction here is 24H2S plus 16H plus 16 nitrates yields to 3 sulfurs, S8 plus 16NO plus 32H2O, and this is the final balanced reaction. Now, when we have a redox reaction in a basic solution, we're going to follow the exact same processes to balance it, except at the very end of each half reaction balancing, we're going to make sure to add hydroxide ions in order to eliminate the hydronium ions that were placed there originally to balance the hydrogen. So we're going to do that first. And once the hydroxides have been added, then we combine both equations and cancel any like terms. So let's get this balanced and processed to that step first, and then we'll combine and show you how this works. So now, since this is a basic solution, we're going to add the right amount of hydroxide ions on each side of each half reaction in order to eliminate the H plus ions. What I mean by that is that if there are two H plus ions present, then we need to add two OH ions in order to cancel them out. Because when H plus and OH react, they make water. And so you'll see here that we rewrite them as water. And then we'll put them together and simplify them. And just like with our acidic solutions, we're going to use a lowest common multiple for the amount of electrons in both half reactions so that when we add them together, they cancel out. In this case, that would be 2. So the full combined reaction, when I multiply the half reaction on the right, which is a reduction reaction, by 2, all the coefficients get multiplied by 2. This is the final simplified reaction where the OHs cancel out and the waters and the electrons cancel out, and our final redox reaction is going to be 2 moles of ammonia plus 2 moles of the chlorate anion yields to 2 moles of chlorine plus 1 mole of N2H4 plus 2OH negative.